Maxwell's equations and get a lot of money also out of that. But let's try to find a simple solution to Maxwell's equations. So, as you know, electromagnetic fields can propagate through empty space, even if there is no sources. We may have antenna there, and then through empty space, air, or even the space, it goes. We can have communications with those space satellites and missions. So let's see, source-free. Space, say, this space is here, which is empty, and our sources are here outside, say our antenna, for example. And then here we have a homogeneous, uniform space, and we ask what kind of solutions to Maxwell's equations are there. So there are no sources, meaning that the current is zero, equivalent to zero, and thus the current density is also, charge density is zero. So it means that we drop this one and we drop this one. Become easier equations. Then, sorry. No. What happened? Like this. But then now you can see that we have electric field E and magnetic field H. And then electric response, the flux density or displacement D, and magnetic flux density B. So this is now the very important connection at what we will talk this week. What is the connection between D to E and B to H?
Minus gradient E.
Hmm?
D égale minus gradient E.
What was that?
French, gradient.
Gradient. Okay. E is minus gradient of phi. That's true. So the gradient, the scalar, right? But now when we are in dynamics, so then no longer we have here the del cross E is no longer zero. If it were zero, we could write E as a function of a gradient of phi. But now I mean this is then the connection between the E field and the response. So that is due to the matter. So if we have material, we have the permittivity epsilon here, and we call it mu here. We call permittivity and permeability. Well, we'll talk about those later. But in fact, I mean, even in free space, there in this relation we say constitutive relation or relations. So if we have a certain material, then the epsilon is dependent on the material response. And very often we say that this is then, there is a so-called free space part, and then there is a relative permittivity, which the relative is dimensionless number. Because now this in SI units, you know, System International units, with this epsilon 0, the so-called free space permittivity is a certain complicated constant and has unit ampere second over voltmeter. Well, but this is just a constant, a unit, fundamental unit, so it doesn't, let not that disturb us at all. The important thing here is that in free space, the E and H are the similar vectors, like very, very same vectors. There is only different units, what you say, what you call those. And similarly also for the mu. Mu would have the relative permeability, and again, let's go down, where then mu0 is another constant. and that is very exact constant. This is just a bit inconvenient to play with those. You can see that the powers are -12 and -7, and then easily if you plug those into your computer code, then it may happen that if you use the some other units, certain numbers become a billion times smaller than the other ones, and then you might get into trouble in balancing just due to the fact that you are playing with different units. And that's why it's very nice to play with relative units, and I'll come back to that later. But now let's still discuss this question about how to solve Maxwell equations, simple solution in very simple medium which is uniform. We have epsilon and mu here, all through this space this box there. It could be free space, air, where it's epsilon 0 and mu 0, but it could be something else. But you can think that it's free space. And now let's, yeah.
One question. Of course, Maxwell's equation give differential relation between, let's say, electric field and, for example, magnetic flux density locally. Okay, but I have also seen these constitutive relations which give relation also for D, like being equal to something times E plus something times E, actually.
So you are talking that here would be something proportional to H.
Yes. So,
right.
So things kind of strange because Maxwell's equations give, let's say, differential relation, but
yeah,
kind of a constitutive relation would give.
That is a very good point. So
what is the
then, okay, that is then certainly a metamaterial, because that would have electric response due to magnetic excitation, and why not vice versa? If we have time later today, let's discuss this thing here. But you can guess that would complicate my aim to find a simple solution. So please bear with me for a couple of hours still. But did you understand an extremely important point what he's saying? That sometimes, I mean, how does the response in matter happen? It means that in empty space there is no matter, so it is just like fixed, and what there is in E, that is exactly the same as D, measured in different units. But if there is say, water is a good example, because water, you have water molecules which are very strange, because they are polar molecules, meaning that they are non-symmetric. There is a permanent dipole moment. So you get electric field there, it gets like polarized and gets a strong electric energy density into the field. But that is electric. But then sometimes, and in metamaterials, you might have that it would get magnetic response and vice versa. And that is, of course, a very important point that you might make use of in applications. Yes, please.
What is this? Can we explain it, for example, that we say permittivity is generally complex?
Oh, that is another point, yes. Perhaps it is not exactly the same, because in the complexity then is connected to the fact that, well, it is not easily seen from here, but normally we say that it is connected to losses. So if we have lossless media, then they are real, the parameters, material parameters that we apply. But losses are extremely important and unavoidable. But they are also the advantage and the power of complex notation is that then these imaginary parts have a very clear meaning with which we can calculate the dissipation parameters. And we will come to that perhaps also today. Okay, but if we deal with very simple homogeneous, meaning that it is the same in every place, and say free space, characterized by this epsilon and mu, then we can simplify the Maxwell's relations here by